the sectorial area traced out by the radius vector to the center of force increase at a constant rate. This is very common and also an important problem of central orbit, and we are going to prove this problem in this class. Okay, what is the answer of this problem? Since it is said that in the central orbit, okay, so we take this is initial line OX and this is the central orbit, and let the particle be at P at any time T. Okay, P r theta at any time T. Let the particle P move to Q in time delta T, T plus delta T, and the coordinate of this point is r plus delta r, comma theta plus delta theta. Okay, so we clearly say that the sectorial area traced out by the radius vector OP is given by this area. Okay, let it be delta A in time delta T, because here the time is T, here the time is T plus delta T. Now, since the particle is in central force, so the force always act along the radius vector and towards the center of force O. Let F be the center of force or central force. So we know that the equation of motion of central force is radial equation of motion, which is named as Fr, and this is r double dot minus r theta dot square. This is minus F. This is first equation, and F theta, this is 1 by r ddt of r square theta dot. This is equal to 0. This is second equation, because there is no force parallel to OP. Right? Now, when the position Q tends to P, that is when Q tends to P, then this angle, this is delta theta, because this is theta and this is theta plus delta theta. So delta theta tends to 0. Also, this is r and this is r plus delta. So we must have delta r tends to 0, and the sector delta A tends to the triangle OPQ. If we draw a chord PQ, right? Triangle OPQ, and the area of this triangle is half into r plus delta r into sine delta theta, because two sides of the triangle is r plus delta r, and this is delta theta. Right? Now the rate of change of sectorial area is delta A by delta T is tends to half r plus delta r into sine delta theta by delta T, and taking limit as T tends to 0, then Q tends to P, and similarly delta theta tends to 0, delta r tends to 0, and we get dA by dt, and this is equal to limit delta r tends to 0, maybe delta theta tends to 0, maybe T tends to 0, or delta T tends to 0, etc. And we get half, we take common half outside the limit, and this is r square sine delta theta by delta theta into delta theta by delta T, and the second term is r into sine delta theta by delta theta into del r by del t into delta theta, right? So the limit is half into, this is 1, this is d theta dt, this is 1, this is dr dt, and for this value this is equal to 0 because delta theta tends to 0. So the limit is half r square d theta dt because the second term is 0, right? Now from the second equation of motion we get r square theta dot, this is equal to h. This is a standard result and h must be constant. By integrating we get this is a standard constant of central orbit and this is the constant term of central orbit. Okay, so we say that dA by dt, this is equal to half into h because r square theta dot, this is equal to h, and r square theta dot we put here, the value is h. Okay, so we say that this is constant and this constant is positive constant because h is positive constant. Okay, and dA by dt, what is dA by dt? This is the sectorial area traced out by the radius vector in time t, or the rate of description of sectorial area. So we say that this is dA by dt is greater than 0 and this is constant, so it increases because it is greater than 0 and at a constant rate because this is constant. So we say that the rate of description of sectorial area traced out by the radius vector to the center of force is increased at a constant rate and it is increases because it is greater than 0. Okay, this is the proof of this problem.